This will just be a very short clip for the end of week 7 that's just going to dip our toes into the concepts associated with logistic regression. Logistic regression is when our dependent variable is a binary outcome. And in this case, we cannot code our dichotomous variable as a 1 and a 2 or a 3 and a 4. It has to be a 0 and a 1. And we want to let the value of 1 equal our category of interest, and 0 will be our reference category. So just remember from linear regression when we had to do that G-1 rule. If we had 4 variables or categories, we would create 3 new variables where 1 would equal our group of interest and 0 would equal our reference category. So when we're looking at the dependent variable, we're predicting the value of 1 compared to our value of 0. So commonly in criminology, we might be looking at recidivism, where 1 equals recidivism and 0 equals not recidivism. In logistic regression, we're going to be estimating the odds that this event occurs. So sometimes it's not an event. We might be looking at predicting whether somebody prefers Coke to Pepsi or vice versa. We're essentially calculating what's called the change in the log odds of the dependent variable. So why do we call it a log odds? Well, our categories are only 0 and 1. But what we can do is we can change that 0 and 1 to essentially a matter of probabilities, where 0 equals a 0 level of probability and 1 equals a perfect probability. When we can transform these probabilities into odds to look at the change in the DV's logged odds. We need to do this because several of the assumptions of ordinary least squares regression or linear regression do not apply. So when we have a dichotomous dependent variable, obviously we no longer have a normal distribution. When we are looking at the linearity between our independent variable and our DV, we don't find this with a dichotomous variable. Similarly, homoscedasticity, normal distribution of residuals, these are all assumptions of OLS that will not apply to logistic regression. So in some ways it's kind of nice because now you don't have to memorize all of these different assumptions, but it does mean that we are doing different procedures. Here are the assumptions associated with logistic regression. So we'll start with the idea that we actually have to have meaningful 0 and 1 categories. We have to remember with the best linear unbiased estimate, we have to be including all relevant variables, and that's the same case here. And we want to have that 15:1 cases to variable ratio just like in linear regression. An assumption of logistic regression is that there's a linear relationship between continuous independent variables and the log odds, sometimes referred to as the logit, of the dependent variable. We also make that assumption of independent observations or independent cases, just like we have for basically all other analyses, an assumption about no outliers, an assumption about no multicollinearity. In linear regression, we were able to check off those boxes that would provide us with information about variance inflation values. When we do this in SPSS, logistic regression doesn't provide us with this box. But if we simply run a linear regression model, so we put our dichotomous DV into the outcome box for a linear regression model, then we can actually look at whether multicollinearity was found or not. With respect to linearity in the logistic regression analysis, when the assumption is violated, the logistic regression analysis will underestimate the relationship between the independent and dependent variables and will lack power. So this is generally associated with type 2 error, which is where we think that there is no relationship, where we say that we fail to reject the null hypothesis when we actually should be rejecting the null hypothesis. One of the things that you can do if you find that you've violated the assumption of linearity is to take that interval level variable and divide it into categories and then treat it as a categorical variable. I haven't mentioned it yet, but what's nice about logistic regression is that you don't have to do the G-1 rule. If you're looking at, say, ethnicity, and you have 3 categories, person that's self-reported being black, Hispanic, or white, then you can actually just enter that categorical variable as is, and then you can let SPSS know which category you want to act as the reference category. When evaluating the performance of our logistic regression model or the fit of our model, we'll look at 3 criteria. The first is Holzmer-Lemmerschau, the second is our pseudo R-squared value, and the third is our receiver operating characteristic, area under the curve, or sometimes just referred to as AUC values. And we'll go through and talk a little bit about each one of these. We use the Holzmer-Lemmerschau test to indicate model fit. Basically, it takes our sample and breaks it down into deciles, so 10 different subgroups, to see if the model is a good fit for within each of these 10 different subsamples of roughly equal size. This is the main goodness of fit test for a logistic regression analysis. It tells us whether our model is properly specified. If the difference between observed and expected values of the Holzmer-Lemmerschau test are off or large, that means the prediction is off. The more of these errors we see, the higher the likelihood of a significant test. So it's kind of like a chi-square test. We're looking at the difference between observed and expected values, but in this case we actually don't want to see much of a difference. In a chi-square analysis, we're testing whether our observed values differ from our expected values, and we might want them to differ because we're expecting or anticipating an association. Here we want to see that our observed and expected values are virtually identical. It's saying that what we observe for the entire sample is basically what we observed in those 10 different subsamples as well. All you have to do for reporting is say whether or not the Holzmer-Lemmerschau test was significant. Non-significant is indicating that the prediction does not vary across your different subsamples. The next fitness test that we can look at is pseudo R-squared, and I actually really hate pseudo R-squared values because there are so many examples of research papers out there that misinterpret the meaning of pseudo R-squared. Last week, and actually kind of this week, we were learning through linear regression the idea about R-squared as giving us an indication of explained variance. And so students might think, okay, so pseudo R-squared is just another way of looking at explained variance. We have adjusted R-squared, and now we can have pseudo R-squared. Here's the thing. Pseudo R-squared has nothing to do with explained variance. In fact, there are all these different sort of metrics or indicators of pseudo R-squared, and some of them actually go above the value of 1. What this means is that if we were interpreting it as explained variance, we could potentially be saying that we have explained more than 100% of our outcome variable, and this is obviously impossible. So pseudo R-squared is just another way of like Cohen's d giving us a sign of the effect size of the overall model. And logistic regression analyses and SPSS allow you to pick different types of pseudo R-squared indicators. I think Nagelkirche is maybe the one most commonly used. So what I say that you should do for your paper is you can just specify the value of Nagelkirche and move on. You don't even need to interpret it, but I want you to know how to do it because some reviewers will expect it. I don't know why they ask for these things because I don't think we can draw much meaning from it. What is much more valuable in terms of assessing model fit and the accuracy or the degree to which we understand our dependent variable is looking at receiver operating characteristic, area under the curve values, which tell us about how sensitive and specific our model actually is. Sensitivity refers to the true positive rate. So how often does the event that we predicted to happen actually happen? Specificity is the true negative rate. We predicted the event to not happen, and in fact it did not happen. So remember, we're coding our DV as 1 and 0. So sensitivity is looking at how often do we predict a particular case to score 1 on the dependent variable. I don't know why I held up 2 there. 1 on the dependent variable, and in fact, the observed value for that case was also 1. Specificity is looking at how often, or what is the rate in which we find that an individual case, their predicted value is going to be 0, and it indeed did not actually happen. Their observed value was also 0. AUC values indicate how well the model is able to distinguish between groups, and this is what's really important. So we want to know how well we're doing at predicting both outcomes, both when the variable is present or when the outcome is present and when it's not present. And the AUC values have more interpretable values as well. So we can, like Cohen's d, we can actually refer to specific benchmarks. Anything above about 0.56 is considered small. Anything from 0.63 so on is moderate. 0.714 is considered to be a large effect size. Anything lower than 0.56 is considered to be trivial or like not a meaningful effect whatsoever. Earlier I referred to how we can think about our dichotomous variable as probability. So if we have a sample where they either scored 0 or 1, if we ran univariate descriptive statistics and our value was 0.323, we could say that the probability of scoring 1 on our dependent variable was 0.323. But then we wanted to look at the log odds. So what's the difference between probabilities versus odds? The difference between probability and odds is that a probability looks at the proportion of cases that were yes or the proportion of cases that were no relative to the entire sample. So for example, here we could look at the number of individuals that recidivated, and we would divide it by all cases, so including those that did recidivate. So if we had 100 cases, 30 of those individuals recidivated, the probability of recidivism would be 30 divided by 100. When it comes to an odds ratio, what we'll be looking at is the number of individuals that did recidivate divided by the number of individuals that did not recidivate. So instead of looking at the denominator having all cases, we're looking at the relative proportion of individuals that did recidivate divided by those that did not recidivate. Let's run through probabilities, odds, and odds ratios with another example. So let's say that we had a sample of 20 individuals, 10 gang members and 10 non-gang members. And we want to look at whether recidivism was more likely for gang members or more likely for non-gang members. What we observed is that 7 of 10 gang members recidivated and 3 of 10 non-gang members recidivated. So we can begin to figure out the odds ratio first by looking at probabilities. So for gang members, 7 out of 10 recidivated, meaning the probability of recidivism was 0.7. We can also say that the probability of non-recidivism would be 0.3. For non-gang members, the probability of recidivism is 0.3, or 3 out of 10 recidivated. That means that the probability of non-recidivism is 0.7, because these probabilities have to add up to 1. So we can use these probabilities to compute the odds of recidivism for each group. For gang members, it's 0.7, the numerator being the probability of recidivism, divided by 0.3, the denominator, or the probability of non-recidivism. So we get the odds of gang members recidivating to be 2.33. For non-gang members, it's the inverse. 0.3 divided by 0.7 equals 0.43. So the odds of a non-gang member recidivating is 0.43. So if we want to figure out the difference in odds, we can't just take 2.33 minus 0.43. We have to compute what's called an odds ratio, where we would divide the odds of recidivism for gang members by the odds of recidivism for non-gang members. So if we do 2.33 divided by 0.43, we would get a value of 5.42. So we would say that for a gang member, the odds of recidivism is 5.42 times higher than the odds of recidivism for a non-gang member. Basically, the two take-home messages from this slide are that first, probabilities, odds, and odds ratios are not the same thing. And the second is that when we're interpreting logistic regression analysis, we'll be relying on odds ratios. When we looked at linear regression, we were interpreting unstandardized coefficients and we were interpreting standardized coefficients. When interpreting odds ratios, sometimes you'll see what's called exponentiated B. Exponentiated B is literally the exact same thing as an odds ratio. It's where we exponentiate the B coefficient. So just like linear regression, logistic regression will produce a B coefficient, but it's very difficult to actually interpret this B coefficient, because remember, the B coefficient is telling us about a 1 unit increase in X on a some unit increase in our dependent variable. But for a logistic regression analysis, remember we transformed our dependent variable to log odds, not a 0 and 1 category. So we're looking at a 1 unit increase in X on a X whatever unit increase in the log odds of our DV, which isn't really something that we can naturally interpret. So in the earlier example, we would say that gang members were 5.42 times more likely to recidivate compared to non-gang members, or we could also say that gang members were 542% more likely to recidivate compared to non-gang members. Where we can run into some challenges is with interpreting odds ratios or exponentiated B values that are less than 1. If we saw an odds ratio of recidivism for persons that were in treatment compared to not in treatment as 0.35, it would indicate that the treatment group, which we coded as 1, were less likely to experience the event, aka to recidivate, compared to the reference group, which was coded as 0. So how do we interpret this? There are two options. So one, we can think about it as a decrease in the likelihood of recidivism for those that experience treatment. So if you want to interpret it this way, if you want to be focusing on that group of interest, that treatment group, those that did receive treatment, and they have a odds ratio of less than 1, to figure out the odds ratio, you just put a 1 in front of the odds ratio. So you take 1 and you subtract the odds ratio value, and now you'll get, in this case, a value of 0.65. So you can say that individuals that attended treatment were 65% less likely to recidivate compared to those persons who were not in treatment. So very, very importantly, if you had just looked at the odds ratio on its own, you'd be wrong to say that individuals in treatment were 35% less likely to recidivate compared to individuals not in treatment. We have to transform the odds ratio if it's less than 1. Another thing that we could do, if we wanted to look at which group was more likely to recidivate, is to take the inverse values, where all we have to do is go, instead of 1 minus the odds ratio, we do 1 divided by the odds ratio. So in this case, 1 divided by 0.35 gives us 2.86. So we could say that individuals that were not in treatment were 2.86 times more likely to recidivate compared to persons that did attend treatment. If you are more interested in interpreting the group of interest for your independent variable, you would go with the first option. If you are more interested in interpreting the group of interest for your dependent variable, you would go with the second option. We will definitely talk more about this in the asynchronous lecture for next week, as well as for the synchronous lecture of that week. But again, I just want students to get exposed to these things early on so they can kind of sit on them, think on them for a little bit, for a week, and then we will reintroduce these key concepts in next week's class. Take care, everyone.